Let's get at her. Chemistry 1411. This is practice exam 2. Let's take a look. Question number 1. It says, with respect to the system only, a reaction with a delta H that is negative or less than 0 and a delta S that is positive greater than 0 is predicted to be, well, for that, we're going to use the formula delta G is equal to delta H minus T delta S, because you can see that we're being asked about the spontaneity of the reaction. So if our delta H is less than 0, we have a negative number. We're subtracting T times delta S. Our T is always a positive number. And if our S is greater than 0, that means that it is a positive number. If you're taking a positive and multiplying it by a positive, that gives you a positive. And so you're essentially doing negative subtract a positive number. So that means that it's always going to give you a negative delta G. Delta G is always going to be negative all the time. So the reaction will be spontaneous at all temperatures, because temperature, again, is always a positive number. And so the answer is A, spontaneous at all temperatures. Question 2, in which of the following is consistent with the spontaneous process in the forward direction? Well, you can see that we're comparing delta S of the universe, delta G, and T times delta S of the universe. Well, we know that when the entropy of the universe is increasing, when it's greater than 0, we're dealing with a spontaneous process. Since temperature is always positive, that means that T, which is positive, multiplied by our delta S of the universe, which is positive, is always going to be greater than 0. So that will be positive as well. Now, we know that delta G, when we have a spontaneous reaction, is going to be a negative number. So it is going to be less than 0. And so the answer that fits the bill for all of these would be C. The delta S of the universe is increasing. The T times delta S of the universe is increasing. It's greater than 0. And delta G is less than 0 when we have a spontaneous forward reaction. Question number 3, we look at this graph. We have delta G naught on the y-axis, and we have absolute temperature on the x-axis. And you can see in this reaction that as the temperature increases, delta G naught becomes more negative, right? It's dropping down and down, so it's getting more spontaneous at a higher temperature. So the question is, which one of the following is an incorrect conclusion based on the information in this diagram? Well, first of all, if the delta G is becoming more negative as temperature increases, that means the reaction is becoming more spontaneous as temperature increases. This is an endothermic reaction, right? The heat could be regarded as a reactant. So endothermic, therefore, delta H is going to be greater than 0. Next, we have delta S is increasing. Well, for that, we can use delta G is equal to delta H minus T delta S. Remember that the reaction is getting more spontaneous, more negative, as the temperature is increasing. So if we have a negative and then we have a positive for our delta H, subtract a positive times something, whether it's a positive or a negative, you can see that as the temperature increases, the delta S is also going to increase to make it more and more negative, right? Because we see that as temperature goes up, in order for delta G to get more and more negative, my delta S has to be a positive number. And so these two are both correct. The next one is the reaction is spontaneous at high temperatures. That is true based off of the graph. As temperature increases, delta G becomes more negative. The next one, it says as delta S increases with temperature while delta H remains constant. Well, we know that both delta S, so for this one, we know that both delta S and delta H naught will remain constant, won't they? They remain constant, because if they didn't, we wouldn't have a linear slope. for this graph. So this is the one that is incorrect. And of course, there does exist a temperature where delta H is equal to T delta S, right? That's when delta G is equal to 0. So this is when delta G naught would be equal to 0. All right, let's move on and talk about entropy. Question number 4, it says arrange these compounds in order of increasing standard molar entropy. You can see that we have two gases, we have a solid and a liquid. Well, you should know that the entropy of a solid is going to be less than a liquid, and the entropy of a liquid is going to be less than that of a gas. So we know that the zinc sulfide is going to have the lowest entropy. The water in the liquid phase is going to have the next lowest entropy. Then if I compare the entropy of these two gases, the first one, C3H8, that's propane gas. The next one is ethane gas, which the names are neither here nor there. But since we have more atoms, right, we have more atoms and more mass overall in the molecule, we have more ways that the molecule can vibrate, and therefore it's going to have a higher entropy than the ethylene gas. So it's going to go C2H4 gas next, and the one with the greatest entropy is going to be the propane gas, C3H8, like that. And so the answer is A. Question number 5, which one of these is going to have the highest change in entropy? Which one is going to have the highest change in entropy? Well, if we look at A, you can see that overall with A, we have 3 moles of gas is our starting material, 3 moles of gas. And at the end, we have 1 mole of carbon dioxide and 2 moles of water. So we're ending up with 3 moles of gas. So there might be a change in entropy here, but it's going to be really slight. If we take a look at C, you can see that we're going from 1 plus 2.5, so that's 3.5 moles of gas. And then we're going to 3 moles of gas. So you can see the entropy is actually decreasing here, right? The entropy is going to be less than 0 in this case, or the change in entropy. In D, I'm going from a total of 4 moles of gas to 4 moles of gas. So that is a scenario that is similar to A. So the change in delta S is going to be very small. So you could just put delta S naught will be very, very small. Okay, delta S naught will be very, very small. But if we look at B, you see that we're going from 1 plus 3.5, so that's 4.5 moles of gas, to 5 moles of gas. So we're actually increasing the number of moles of gas, and therefore the disorder or the entropy is increasing. And so the delta S in this case is greater than 0. It's got the greatest change in entropy. And so the answer is B. Number 6, it says predict the signs of delta H, delta S in that order for this reaction. So we have oxygen, O2 gas. So we have O2 gas, and it's producing 2 moles of oxygen atoms in the gaseous phase. Well, what's happening here? We know that our delta S is going to be greater than 0. The entropy is increasing because I'm going from 1 mole of a gas to 2 moles of a gas, right? So I have more particles, more possible microstates, so entropy is increasing. So my delta S is going to be a positive number. What about my delta H? Well, from General Chemistry 1, you know that O2 has a Lewis structure that looks like this, right? There is a bond that has to be broken in order to make 2 separate oxygen atoms. And therefore, we're going to have to put energy in, right? We're going to have to put energy into the system. We're going to have to put heat into it. So my delta H is also going to be a positive number. I have to put energy into both of those. And so the answer is C. Both delta H and delta S are going to be positive values. The entropy is increasing, and this is an endothermic reaction. I could put that on here too, endothermic. I have to put energy in to break the bond. There's no bonds when I have 2 free oxygen atoms. Question number 7. Which response includes all the following processes that are accompanied by an increase in entropy? Well, if we take a look at number 1, we have 2 moles of gas being converted into 2 moles of, sorry, if we have 3 moles of gas, sorry, I can't count. We have 3 moles of gas being converted into 1 mole of gas. So we're going from 3 moles of gas to 1 mole of gas. And so that is definitely not an increase in entropy. That is, in fact, a decrease in entropy. If you look at the second one, we're going from a liquid to a solid. That is also going to be a decrease in entropy. If we go to the third one, we're going from a liquid to a gas, which is going to be an increase in entropy. So that's a good one. And then in the last one, we're going from hydrogen peroxide in the liquid phase, and then we're producing 2 different molecules. One's a liquid and the other one's a gas. And so our entropy is certainly increasing. We're going from a liquid to a liquid and a gas, right? Not only do we have more particles, but one of them is a gas. And so the randomness or the disorder is increasing. So the answer is B. Numbers 3 and 4 represent increases in entropy in these reactions. Question number 8, same thing. Arrange these reactions according to increasing delta S. If we look at the first one, we're going from a gas to a liquid. That is going to be a decrease in entropy. If we look at the second one, you can see that we have 2 moles of gas as a reactant, and we have 2 moles of gas as product. So we're going from 2 moles of gas to 2 moles of gas. And so our delta S would be very small in this case, probably no change. In the next one, we're going from a solid magnesium carbonate, and we're producing magnesium oxide plus carbon dioxide gas. So not only do we have 2 particles, but we're also producing a gas. And so there's going to be an increase in our entropy. So we can see that if we're going to list these according to increasing delta S, number 3 is going to have the greatest entropy. You can see that this one was actually decreasing. So number 1 is going to be the lowest. And number 2, I said, since we're going from 2 moles of gas to 2 moles of gas, the delta S is going to be really small. So something like that. So we have 1 being lowest, 2 intermediate, and 3 is the increase. And so the answer in this case would be C. Next one, we're just going to take a look at these compounds and determine which one has the highest standard entropy. Remember that even though each one of these is composed of just carbon and hydrogen, these are all what we call hydrocarbons, the one with the highest entropy is going to be the one with the most atoms and bonds. Okay, and it's pretty clear that the one that has the most atoms and bonds in it is going to be the C3H8, which happens to be propane, but it is a gas. Also, you can see that all of them are a gas, so we're going to have to go with atoms and bonds. And so the answer is C. It's the one with the most atoms and bonds. It can vibrate in the most different possible orientations, and so it's got the most disorder. Question number 10, it says, using the thermodynamic data provided below, calculate the KSP for zinc sulfide at 25 degrees Celsius. So you guys should remember KSP. So we have zinc sulfide in the solid phase, which is in equilibrium with some zinc ions in the aqueous phase, plus sulfide ions in the aqueous phase. If we wanted to evaluate the KSP, we would have to take a look at the concentration of zinc ions multiplied by the concentration of sulfide ions. We don't include zinc sulfide because it's a sulfide, or a solid, sorry. Anyhow, so we're going to use the formula delta G naught is equal to negative RT times the ln of K, and that K is going to be our KSP. Well, we don't have delta G, but we do have delta H of formation values and standard entropy values. Using those, we can figure out the delta H of the reaction, the delta S naught of the reaction, and we can use that to calculate the delta G at 25 degrees Celsius. So first, we're going to calculate the delta H of the reaction, which is going to be the sum of the enthalpy of the products, subtract the sum of the enthalpies of the reactants, of course, multiplied by their stoichiometric coefficients. So for my zinc ion and my sulfide ion, I have negative 152.4 plus 41.8. And of course, that's kilojoules per mole. I'm going to put that in the end, subtract negative 203 for my zinc sulfide kilojoules per mole, and I end up with a delta H naught for my reaction, which is equal to 92.4 kilojoules per mole. I'm going to do the same thing for my delta S naught of the reaction. I use the exact same thing. We take the standard entropies of the products multiplied by their stoichiometric coefficients. Everything is 1 here. Subtract the standard entropy of the reactant. So I plug in my numbers. I get negative 106.5 for my zinc ion plus 22. Subtract 57.7, and the units here are joules per mole times Kelvin. And when I punch that spinach into my calculator, I get a delta S naught for my reaction as being negative 0. So I actually end up with what? I end up with negative 142.2 joules per mole Kelvin, which is the same thing as negative 0.1422 kilojoules per mole Kelvin, right? Because there's 1,000 joules and 1 kilojoule. So I just did the conversion there. Now that I have my delta H and my delta S, I can solve for my delta G. And my delta G naught is going to be equal to delta H naught minus T delta S naught. I know my delta H, which is 92.4 kilojoules per mole. Be sure you're confident in your units here. I'm at 25 degrees Celsius, which is 298 Kelvin, multiplied by my delta S, which is negative 0.1422 kilojoules per mole Kelvin. Put all that in brackets. And then my delta G ends up being, my delta G naught for my reaction is 134.8 kilojoules per mole. Now I can use this formula to solve for K. That's something that we did in class. You should be able to say delta G naught is equal to negative RT times the ln of K. The ln of K is equal to negative delta G naught over RT. So K is equal to e to the power of negative delta G naught over RT. Now we can just plug our numbers in. We have negative 134.8 kilojoules per mole divided by R, which is 8.314 times 10 to the negative 3 kilojoules per mole Kelvin, right? We have to put to the negative 3. It's not 8.314 joules per mole Kelvin. We want to convert it into kilojoules because I have kilojoules up here, multiplied by my temperature, which is 298 Kelvin, like that. You can see that kilojoules cancel, moles cancel, and Kelvin cancel. We end up with our K being equal to e to the power of negative 54.4, and therefore our K is equal to 2.4 times 10 to the power of negative 24, like that. So 2.4 times 10 to the power of negative 24, so we have A. Question number 11, using the thermodynamic data provided here, calculate Ka1 for carbonic acid, H2CO3. Ka1 is the dissociation constant of the first proton, right? The reason it says Ka1 and not Ka is because there's 2 protons, right? Ka1 is the first proton being lost. Ka2 would be the second proton being lost. So Ka1 would be the carbonic acid in equilibrium with the proton from the first acidic proton plus the bicarbonate ion, like that. So that's our Ka1 expression. We're asked to calculate the Ka1. And so the way that we're going to do that is we're going to use the formula delta G naught is equal to negative RT ln K. We're going to solve for delta G, and then that's going to enable us to calculate the K, which in this case is Ka1. So the question then becomes, how do I calculate delta G? Well, I'm given delta H of formation values and delta S values the exact same way I was in the previous problem. So to figure out the delta G, I do the same steps I did in the last problem. First, I'm going to calculate my delta H naught of reaction, which is going to be equal to negative 691.11 subtract negative 698, 698.7, and that's all kilojoules per mole, and that gives me 7.59 kilojoules per mole as my delta H. I'm going to calculate my delta S, exact same strategy that I did in the last problem. I have 95.0 from my bicarbonate ion, subtract 191, and this is in joules per mole Kelvin for the whole dang thing, and I end up with a delta S, which is, it would be negative 96 joules per mole Kelvin. I'm going to convert it directly into kilojoules, which would give me negative 0.096 kilojoules per mole Kelvin. Notice that I skipped a step here, right? I went from joules and then I did the extra step of dividing by 1,000 to give me kilojoules per mole Kelvin. I need to have those units consistent for calculating my delta G. My delta G naught is equal to delta H naught minus T times delta S naught. So I have my delta H, which is 7.59 kilojoules per mole. Subtract, temperature is 25 degrees Celsius or 298 Kelvin, multiplied by negative 0.096 kilojoules per mole times Kelvin. Like that, you can see that Kelvin cancels out. I end up getting a delta G naught value, which is equal to 36.2 kilojoules per mole. In the interest of time, I'm not going to derive the equation that we did in the last problem. Question 10, we said that K is equal to e to the power of negative delta G naught divided by RT. I plug in some values here. I've got negative 36.2 kilojoules per mole divided by 8.314 times 10 to the negative 3 kilojoules per mole Kelvin, multiplied by 298 Kelvin, like that. That gives me K is equal to e to the power of negative 14.6. I end up with my K as being equal to 4.5 times 10 to the negative 7, which is going to round up to having only one sig fig. You see that all the answers have only one sig fig, and so that's going to give me, where am I, 5 times 10 to the negative 7, which is C. All right, got those two done. Number 12. For the reaction 2NO plus O2 gives you 2NO2. If initially you have a pressure of 1.5 atmospheres for NO, 1.4 atmospheres for oxygen, and 2 atmospheres for NO2, calculate the delta G. It's not delta G naught, just calculate the delta G for this reaction. So these are non-standard conditions. Right? It's telling me that I have 2NO gas plus oxygen gas produces 2 moles of NO2 gas, and it gives me the pressure of each one of these. The pressure here is 1.5 atmospheres. The pressure here is 1.4 atmospheres, and the pressure of my NO2 is 2.0 atmospheres. I'm going to need to have Q in order to solve this problem, because I know that delta G, which is what I'm looking for, is equal to delta G naught plus R times T times the ln of Q. And Q is going to be equal to the pressure of NO2 squared divided by the pressure of NO squared multiplied by the pressure of O2. I've gone ahead and done that already, which is 2.0 squared divided by 1.5 squared multiplied by 1.4. And when you punch all that spinach in your calculator, you end up with 1.27. So that's my Q value. Next, I need my delta G naught value, don't I? I've been given delta GF values. So my delta G naught for this reaction is going to be equal to the delta G of formation of the product, NO2, multiplied by its stoichiometric coefficient. So I have 2 times 51.8, subtract the delta G of formation of the reactant, NO, multiplied by its stoichiometric coefficient. So 2 times 86.7. Notice that this is in kilojoules per mole. Also notice I don't have a delta GF for oxygen because it's in its standard state. It would be 0. And so I get a delta G naught for my reaction is being equal to negative 69.8 kilojoules per mole. Now I have my, sorry, did I say delta G? Yeah, I have my delta G naught value, and I have my Q value to plug into here and here. So let's do it. My delta G for my reaction is going to be equal to negative 69.8 kilojoules per mole plus 8.314 times 10 to the negative 3 kilojoules per mole Kelvin. Again, I use kilojoules because I have kilojoules over here, multiplied by the temperature, which is 298 Kelvin, 25 degrees Celsius, multiplied by the natural logarithm of 1.27. I'm going to skip some of the math here and just tell us that the delta G is going to be equal to negative 69.2 kilojoules per mole, like that. There we go. So you can do the rest of the algebra yourself, and you see that the answer is D for this question. Question 13, calculate the equilibrium constant for the decomposition of water, given that the delta GF of water is equal to negative 237 kilojoules per mole. Well, if I want to know the equilibrium constant for the decomposition of water, which is this reaction, excuse me, right here, I'm looking for the K. K is equal to what? And all I'm given is the delta G of formation of water. Well, I can use the formula that K is equal to e to the power of negative delta G divided by RT if I had the delta G naught of the reaction. Well, you should know that the delta G formation of H2 and O2 are both going to be 0, right? This and this are going to have a delta G naught of formation, which is equal to 0 kilojoules per mole, or any unit for that matter. And so if I want to calculate the delta G naught of this reaction, it's going to be equal to 0 subtract, make a mistake here. So it's 0 subtract 2 times negative 237.2 kilojoules per mole. I just noticed a mistake in my answer that I wrote down. So I'm going to double check myself here, and I might have to come back on this one, which really sucks. So I have 0 subtract negative 237, so it's 237.2 times 2, which would give me 474.4 kilojoules per mole. Okay, so then I would just use that number. So K is going to be equal to E to the power of negative 474.4 kilojoules per mole divided by 8.314 times 10 to the negative 3 kilojoules per mole Kelvin multiplied by the temperature, which is 298 Kelvin. Like that. You can see that my units cancel. And again, I don't know if this is going to give me the right answer or not, because I think I made a mistake in my algebra before. Let's see here, divided by 8.314 times 10 to, shoot. Let's see here, 474.4 divided by 8.314 times 10 to the power of negative 3 times 298 gives you, yeah, I don't know here, negative 191.5. K is going to be equal to, gives you, I get 7 times 10 to the negative 84 in this case. I'm going to have to come back to this one. Number 14. Calculate the delta S naught for the reaction SO2 solid plus NO2 gives you SO3 plus NO. So we want to know the delta S naught of the reaction. This is something that we've already done. We know that delta S naught of the reaction is equal to the sum of the stoichiometric coefficients of the delta S values of the products, subtract the sum of the stoichiometric coefficients multiplied by the delta S values of the reactants. So again, something that we've done a bunch of times. So we have SO3, which is 256.2 plus 210.6 for our products. Subtract SO2, which is 248.5 plus NO2, which is 240.5. And when we work all that spinach out, we get our delta S naught of reaction is negative 22.2 joules per mole Kelvin, as that is the unit, joules per mole Kelvin, like that. And so there we go. Number 14. So number 15, consider this reaction. Carbon monoxide plus 2 moles of hydrogen gives you methanol. Delta G of formations are provided. Delta HFs are provided. Standard entropy values are provided. And it says calculate the standard entropy of hydrogen. Okay, we're asked to calculate the standard entropy of hydrogen. Well, we know that the change in entropy for the reaction, right? The standard change in entropy for the reaction is going to be 2 times the S naught of methanol. Shit, why did I put a 2 there? Is S of methanol, subtract the standard entropy of carbon monoxide, subtract 2 times the standard entropy of H2. So we'll call this thing here, we'll call this 2x, and x will be the standard entropy of H2. That means that we need the delta S of this reaction in order to determine the standard entropy of the hydrogen. Well, how are we going to get the delta S value? We don't have the standard entropy of hydrogen, so we can't calculate it just using these values. That means that we're going to have to calculate delta G first, delta H second, and then use delta G is equal to delta H minus T delta S to solve for the delta S naught, and then plug that value into here, and then solve for the 2x. If you're not sure what I mean, follow along with me here. First, we're going to calculate the delta G naught of the reaction, and again, same thing we've done a bunch of times. So we have negative 166.3, subtract negative 137.3. Remember that H2 isn't going to have a delta G or a delta H because it's in its standard state. So we have that. We have negative 29.0 kilojoules per mole. We'll do the same thing for delta H. So the delta H of our reaction is going to be equal to negative 238.7, subtract negative 110.5, and again, this is in kilojoules per mole. We get negative 128.2 kilojoules per mole. We have delta G naught is equal to delta H minus T delta S. So that means that T delta S naught is equal to delta H naught minus delta G naught. Delta S naught is equal to delta H naught, subtract delta G naught divided by T. We can plug in some numbers now. We have negative 128.2 kilojoules per mole, subtract negative 29.0 kilojoules per mole, divided by the temperature, which is 298 Kelvin, and we end up with a delta S naught for the reaction, which is equal to negative 0.33 kilojoules per mole Kelvin, which is the same thing because delta S is usually reported in joules per mole Kelvin. So it is equal to negative 332.9. I just added an extra 2 sig figs here. It's just taken off of my calculator. Joules per mole Kelvin, right? I could have written this as negative 0.3329 either way. Doesn't matter. So now I can plug in some numbers here. because I'm given my S naught values. So I have the S I have this formula right here. I'm going to copy it. So copy. I'm going to paste it down here for instructional purposes only. So paste that in. And we get the delta S of our reaction, which is equal to negative 332.9 joules per mole Kelvin, is equal to 126.8 subtract 197.9 plus 2x. And of course, this is all in joules per mole Kelvin. So now all I have to do is solve for x. I end up with negative 332.9 joules per mole Kelvin is equal to negative 71.1, subtract 2x. And of course, this is all joules per mole Kelvin. I end up with 2x is being equal to 261.8 joules per mole Kelvin. I divide both sides by 2, and I get the x, which is equal to the standard entropy of hydrogen. Standard entropy of hydrogen is equal to 131 joules per mole Kelvin, like that. So there we go. So it should be 131 joules per mole Kelvin. Number 16. Now we're into electrochemistry. Which of the following is true concerning a galvanic cell? If we have a galvanic cell, we have an anode on the left-hand side. This is where oxidation occurs. And then we have electrons that are going to flow in this direction towards the cathode, which is where reduction is going to occur. Now, we have a bunch of different options here. Oxidation occurs at anode, reduction occurs at cathode. Well, if we look at C, it says reduction occurs at the cathode. That makes sense because we know that we have anox and red cat, so the reduction occurs at the cathode. That is correct. And then it says this is where cations move towards. Well, that makes sense because if electrons are flowing in this direction, that means that overall I would be building up negative charge on this side of my galvanic cell as negative charge goes in here. And so the cations that are in solution are going to move towards the anode. And so the correct answer would be C. Reduction occurs at the cathode and anions move towards it. Number 17, it says, consider an electrochemical cell constructed from the following half cells linked by a KCl bridge. You have an iron electrode in a 1 molar iron to chloride solution and a nickel electrode in a 1 molar nickel to nitrate solution when the cell is running spontaneously. So they tell us that the cell is running spontaneously. Which choice includes only true statements and no false ones? If the cell is running spontaneously, this means that the standard cell potential must be positive. If we look at these two standard reduction potentials, so let's look at iron 2 first. We take iron 2 plus 2 electrons, gives us iron, which is a solid. The standard reduction potential is negative 0.447 volts. Again, you'd have to look this up from a table, which I will provide on your handout. If you do the same thing for nickel, nickel 2 plus 2 electrons produces nickel in the solid phase. The standard reduction potential is negative 0.257 volts. If E naught cell, the standard cell potential, is equal to the E naught of the cathode subtract E naught of the anode, that tells us that this is going to have to be the anode, because if I subtract that negative number, it's going to give me a positive number. Let me prove it to you. I take negative 0.257 volts, and I subtract negative 0.447 volts, and I end up with a standard cell potential, which is equal to 0.190 volts. So therefore, this is going to be a spontaneous reaction. So now I know what the anode is, and I know what the cathode is. So what's going to happen then is that electrons are going to go from the anode toward the cathode. So the answer is going to be D, where the nickel electrode is going to end up gaining mass, and the nickel electrode is going to be the cathode. All right, there we go. Move on to question 18. Calculate the standard cell EMF, which is just the same thing as standard cell potential. I had that on one of my slides. I said the cell EMF is the same thing as the standard cell potential for the following cells. We have magnesium in Mg2+, we have nitrate ion in an acidic solution, we have NO gas, and we have a platinum electrode. Well, the first thing I would do is look up the standard reduction potentials for both of these, right? Because I know that on this side of my salt bridge, I have my anode, and on the right-hand side of my galvanic cell, I have the cathode. And I know that E naught cell is going to be equal to the standard reduction potential of the cathode, subtract the standard reduction potential of the anode. Let's take a look at the anode first. If you look up in the table, you see Mg2+ plus 2 electrons produces magnesium. The standard reduction potential is negative 2.372 volts. If you look up the standard reduction potential of NO3 minus, it's NO3 minus plus 4H plus, and this again comes from the table, plus 3 electrons gives you NO plus H2O. Anyhow, this is just the standard reduction potential from the table. You get E naught is equal to 0.957 volts. So then we use this formula, and we can say that E naught cell is equal to 0.957 volts, subtract negative 2.372 volts. We get that our standard cell potential is equal to 3.33 volts, which is A. So just a matter of figuring out which side is the anode, which side is the cathode, applying this formula, and being able to look up standard reduction potentials in the table. And again, I will provide you with a table of standard reduction potentials. Question number 19. Complete and balance the following redox equation. The sum of the smallest whole number coefficients is, and we're balancing it in basic solution. So basic solution, the last step is we're going to add hydroxides to cancel out the protons. So let's write out the two half reactions. I don't have a lot of space here, but you see that the bromine has an oxidation number of 0 here. In the bromate ion, it's +5, and in bromide, it's -1. So I'll start by writing out the oxidation, which is bromine producing BrO3 minus bromate. The first thing I'm going to do is balance the oxygens. The first thing I'm going to do is balance out the bromines, because the bromines are unbalanced. Just give me a second to move this over. I have 2 bromines in the reactant, so I'm going to put 2 bromines here in the products. Next, I'm going to balance the water. I have a total of 2 times 3, so I have a total of 6 oxygens. So that means I'm going to need 6 water molecules over here. Next, I'm going to balance out the hydrogens. I have a total of 12 hydrogens here, so I'm going to put plus 12H plus here. Next, I need to balance out the charge. On this side, I have a charge of 0. Here I have 2 times -1, so that's -2 plus +12, which gives me +10. So to get 0, I have to add 10 electrons to this side. Next, I'm going to balance the reduction. So I have my bromine. Maybe I'll use a different color. I have my bromine, which is giving me a bromide. First, I'll balance the bromines. Next, I'll balance the electrons. There is no hydrogens. There is no oxygens to balance. So I just have 2 electrons plus bromine like that. In order to get the electrons to cancel, I have to take the second equation and I have to multiply it by 5, which would give me 10. I'm gonna copy this. I'm gonna copy this one because it remains unchanged, and that will hopefully make it a little simpler. So I'll paste this down here. So I'm not going to change that one. Okay, and I'm going to multiply the second one by 5, which gives me 10 electrons plus bromine, producing 10 bromides, like that. There we go. Now I can tally these two up, and when I tally them up, look, my 10 electrons cancel from both sides, and I end up with a reaction that looks like this. I have, did I forget to multiply that by 5? I did. There we go. So when you multiply 1 by 5, you end up with the number 5. Just telling you guys. Okay, you guys are so polite. Nobody stopped me. Anyhow. So here, what do we get? We get 6 bromines. So we have 6 Br2 molecules, right? I'm adding these together. 1 plus 5 gives you 6, plus the 6 water molecules produces 2 bromate ions, plus 10 bromides, plus 12 protons. So this is done in acid. Now to do the same thing in base, what we're going to do is we're going to add 12 hydroxides to each side to cancel out all the acid. So we're going to add 12 hydroxides here, and we're going to add 12 hydroxides on this side. These are going to combine to give me 12 H2O molecules. I have 6 H2Os over here, so 6 of these are going to cancel to give me 6 water molecules over here. And so my final reaction is going to be 6 bromines plus 12 hydroxide ions produces 2 bromates plus 10 bromides plus 6 H2O. Now notice it says, what is the smallest number of whole number? So complete and balance the following redox equation. The sum of the smallest whole number coefficients is. You probably noticed that this isn't the smallest whole number coefficients. You can take this whole thing and divide it by 2 to give you 3 bromides plus 6 hydroxides produces 1 bromate plus 5 bromides plus 3 water molecules, and that is completely balanced. So if we tally up all the stoichiometric coefficients on the reactant side, we have 3 plus 6, which is 9. Over here we have 6 plus 3, which is 9. 9 plus 9 gives us 18. So that is the sum of all of the coefficients, and so the answer is 18D. Number 20, determine the cell diagram for the reaction below. Assume a platinum electrode is used when no other solid is present. Yeah, okay, so we have our iron 2 plus. So we have 2 iron 2 plus aqueous plus lead 2 plus aqueous, producing 2 iron 3 plus aqueous plus solid lead. Let's figure out what the anode and cathode are. You can see that the iron is going from +2 to +3. Therefore, it's losing electrons. Losing electrons is oxidation. Therefore, this is the anode. It is being oxidized. We have lead 2 plus going to lead 0. And so that is gaining electrons. So this is reduction. This is our cathode. So what do? On the left-hand side, we put our anode. Now, notice that our anode goes from an aqueous solution to an aqueous solution. So we're going to need a platinum electrode on that side, right? We're going to need an inert electrode, which is platinum, which is not in the same phase as the iron 2 plus ions and the iron 3 plus ions, which make up, again, our anode. Then we have a salt bridge that's going to separate them. And in our cathode, we have lead 2 plus, which is going to get reduced to solid lead. Again, this is our anode over here. The reason I had to put the platinum over here is because both of these are in aqueous solution. We have to have an inert electrode when both species involved in the redox reaction on the in the anode are aqueous solutions. Then we have our salt bridge, and then we have our lead, which is being reduced to solid lead. So there we go. This is B. This one right here. Number 21. Complete and balance the following redox equation using the lowest possible combination of whole numbers. So we're going to balance this redox equation. We have bismuth, which has a +3 oxidation state. We have tin in SnO2 2-, which has a +2 oxidation state. We have bismuth here, which has a 0 oxidation state. And tin in SnO3 2- has a +4 oxidation state. So you can see that the bismuth is undergoing reduction. So this is my cathode. And we can see that the tin is undergoing oxidation. So this is my anode. All right. So let's do the oxidation reaction first. We have SnO2 2-, which gives you SnO3 2-. There's no balancing of the tin that's required, but I have one extra oxygen on this side, so I'll put a water molecule over here. I have 2 hydrogens over here, so I'm going to balance that out with 2H+ over here. Now I need to balance out my charge. On this side, I have 2- overall. On this side, I have 0 because 2+ and 2- give you 0. So I need to add 2 electrons to this side. It makes sense because oxidation is losing electrons and the tin is being oxidized and we're losing electrons. Now let's do the reduction. I have the bismuth hydroxide, which is producing bismuth like that. I don't need to balance the bismuth. That is totally fine. I have a total of 3 oxygens on this side. So I'll add 3 water molecules to this side. Now I have 6 protons over here. So I'll add 6 hydrogen ions over here. I have a total of 6+ over here and I have a total of 0 over here. So I need to add 6 electrons to this side. Now what I need to do is I need to multiply this reaction by 3 in order to make this reaction 3H2O plus 3SnO2 2- produces 3SnO3 2- plus 6H plus 6 electrons. Now I can tally up these two equations. When I do that, when I add those two together, what cancels? You can see that I have 3 water molecules here and 3 water molecules here. I have 6 electrons here. I have 6 electrons here. I have 6 protons here and 6 protons here. So everything cancels except for what was present in the initial equation. So I end up with bismuth hydroxide plus 3 SnO2 2- producing 3 SnO3 2- plus bismuth, and that is E. Because it says for the free hydroxide, if we wanted to balance it in base, so that would be in base, how many hydroxides do I need? Since no H+, no hydroxide required in this case. So done. The answer is 0 because hydroxides are not going to be part of the balanced equation. Number 22, the half reaction that occurs at the cathode during the electrolysis of copper to chloride is, well, if I take a look at copper to chloride, and it's in an aqueous solution, I've got copper to chloride, which is an aqueous solution, which means I've got copper 2+ ions, and I've got chloride ions in solution. Oop, need to balance that out, don't I? There we go. So what's going to happen at the cathode is going to be reduction. Which one of these is going to be reduced? Well, I'm not going to reduce this because it's got a negative charge. I can reduce the copper 2+ ions though, can I? So my reduction is going to be copper 2+ plus that one of the answers? The half reaction. Sorry, I'm missing copper 2 plus. Well, I thought I had the standard reduction of the whole copper 2 plus ion, but I guess the only one here that makes sense, since you're starting it with copper 2, right? This is copper 2 chloride. You're going to have to start it with copper 2 chloride, which is going to get reduced, and they're just showing it being reduced to copper 1. So copper 2 plus an electron producing copper 1 ions like that. Yeah, it's the only one that makes any sense. Sorry, that was just my knee-jerk reaction to think that they were going to show the entire reduction. But again, it's the only one that makes any sense because you're starting with copper 2, and it's the only thing that can be reduced. You can't reduce chloride. So yeah, there we go. Okay, anyway, let's see. Let's move on from there. Let's take a look at question number 23. It says, consider the following standard reduction potential. So these are given to you. You don't even have to look them up. The strongest reducing agent among the above is, well, you remember that when we look at the table of standard reduction potentials, whether it's, and I posted a couple different ones in the slides, and then there's one at the back of our book, right? We said that the more positive ENA is, the stronger the oxidizing agent. And I showed you a table, or I posted in the slides, a table. They had oxidizing strengths listed in order. So the cell potentials, the highest ones are at the top with, fluorine or whatever. And then down at the bottom, you had like lithium. So that means the more negative the ENA is, it means it's going to be a stronger reducing agent. Now remember, if we're asked to figure out which one is the strongest reducing agent, so the strongest reducing agent, and in the process of reducing, it means the reducing agent will be oxidized. And the reason I'm putting that in there is because you might just say, well, if I look at this one, it's got the lowest standard reduction potential, therefore it's aluminum, 3 plus ion. No, because if it's causing reduction to occur, it's going to be being oxidized. So the reaction is going to be going in this direction. And so it's solid aluminum that gets oxidized and thus in turn affects the reduction. Okay, there we go. So the answer is the solid aluminum, E. Let's move on to question 24. Question 24, I don't ask a question exactly like this one in our exam. I asked something that's in the same vein on the actual exam, but it's not exactly like this. This is covered in section 17.7. In our textbook, they go over the electrolysis of aqueous sodium chloride. So it's going to be very similar here. It says, predict the products of the electrolysis of aqueous potassium chloride. So let me run it by you here. We have aqueous potassium chloride, which is going to give us potassium ions plus chloride ions. Okay, it's pretty obvious that the chloride ions are the ones that are going to undergo oxidation, right? Because they already have a negative charge. Okay, so at the anode, we can have oxidation. This is oxidation of the chloride ion, or since it's an aqueous solution, we're in water, the water could also undergo oxidation. And if you look up the table of standard reduction potentials, you can see the oxidation of water is H2O, which gives you O2 plus 4H plus 4 electrons. Okay, but the chloride is going to get oxidized, and so we're going to end up having chlorine in there. If we look at what happens at the cathode, which is where reduction occurs, we have our potassium ions, which you might think, okay, well, I have potassium plus an electron is going to give me potassium solid. But if you look at the standard reduction potential of potassium ions, it's what is it? Negative 2.93. It's super negative. Whereas if you look at the reduction of water, which is 2H2O plus 2 electrons gives you H2 gas plus 2OH minus, you see that the standard reduction potential is, shoot, did I not write it down here? Damn it. It is negative 0.8277. So it's negative 0.8277 volts. So since this one is so much less spontaneous, right? Its standard reduction potential is so much lower, then at the cathode, this is going to be the preferred reaction. It's going to be the reduction of water, which means we're going to end up with H2 and 2OH minus in our reaction. And I'm not going to do it right now because I don't have time, but if you compare the spontaneity of these two reactions, you're going to see that the chloride is going to be preferentially formed over oxygen and protons. And so the three species that we're going to end up with are going to be chlorine gas, hydrogen, and hydroxide. This is called the chlor-alkali process. Again, I don't ask a question exactly like this one, but I asked something in a similar vein that's actually a little bit simpler. All right, let's take a look at question number 25. It says calculate the cell EMF, which is the same thing as the standard cell potential for the following reaction. We have two silver plus ions with a concentration of 0.010 molar plus hydrogen with a pressure of 1 atmosphere, which produces two silvers solid plus 2H plus, and I have a pH which is equal to 6.0. From my pH, I can calculate the concentration of the H plus because it is aqueous, right? It's in a solution. Let me just tidy this up a little bit. So we have our H plus, which is aqueous. Because I know that pH is equal to negative log of the concentration of H plus, I can say that the concentration of H plus is equal to 10 to the negative pH. And since my pH is equal to 6.0, I say the concentration of H plus is equal to 10 to the negative 6.0, which gives me the concentration of H plus, which is 1.0 times 10 to the power of negative 6 molar. So I can put that in here, 1.0 times 10 to the negative 6 molar, like that. You can see that I'm not at a standard concentration for my hydrogen ions. I'm not at a standard concentration for my silver ions. So I'm not calculating E naught cell am I? I'm going to be calculating the E of the cell, right? And I know that in order to calculate the E of the cell, I need the standard cell potential, subtract negative 0.257 volts divided by N times ln of Q. Well, how many electrons are being transferred? If I'm going from 2 silver plus ions to 2 silver 0, and from H2 to 2H plus, that means that 2 electrons are being transferred. My N is equal to 2. So I know what my denominator is. Now I can solve for my standard cell potential, E naught cell, by looking up the values for the table. I'm not going to do that. I'm not going to write down the standard reduction potential reactions for both of these, but it's E cathode minus the E of the anode. And I end up with 0.80 volts, subtract 0 volts, because this is the standard hydrogen electrode. And I end up with an E naught cell, which is equal to 0.80 volts. So now I have this value. I have this value. I just need to work out my Q. Well, from my reaction, I can see that my Q is going to be equal to the concentration of H plus squared divided by the concentration of the silver ions squared multiplied by the pressure of the hydrogen. When I punch all that spinach into my calculator, you get 1.0 times 10 to the negative 6 squared divided by 0.010 squared multiplied by 1. That gives you a Q, which is equal to 1.0 times 10 to the negative 8. Now we can plug everything into our equation because now we also have our Q. I shouldn't have used a green highlighter, huh? There we go. We also have our Q. Let's do it. So we have our E for this cell, which is non-standard, is equal to 0.80 volts, subtract 0.0257 volts, divided by 2, multiplied by the natural logarithm of 1 times 10 to the negative 8. When we do that, we get E is equal to 0.80 volts, plus 0. I can't even read my own writing. I think it's 237. No. .236 volts, so it's 0.236. 236 volts plus 0.8, and I end up with 1.04 volts. So 0.236 volts, and I end up with my E as being 1.04 volts, which is B. There we go. How many questions do we have left? 26, 27, 28, 29, and 30. Okay, so we have a few more questions. Well, let's solve 26. For the electrochemical cell shown here, determine the equilibrium constant for the reaction. Well, let's write down what we know. We have cadmium in the solid phase. We have cadmium 2 plus, aqueous phase, separated by a salt bridge. Then we have cobalt 2 plus in the aqueous phase, and we have solid cobalt after it's reduced. So this side here is our anode. This side here is our cathode. Our E standard reduction potential for the anode reaction is negative 0.403 volts. For the cathode, E, the standard reduction potential is negative 0.28 volts. My standard cell potential, which is the E naught of the cathode, subtract the E naught of the anode, is going to be equal to negative 0.28 volts, subtract negative 0.403 volts. I get my E naught cell is being equal to 0.123 volts. Like that. I'm asked to calculate the K equilibrium. I know that E naught cell is equal to 0.0257 volts divided by N multiplied by the ln of K. So I can solve for K pretty quickly. But how many electrons are being transferred? Well, if cadmium is being oxidized to cadmium 2+, I'm transferring 2 electrons, right? And I'm losing 2 electrons, and then I'm gaining 2 electrons here. So N is equal to 2. So N is equal to 2 electrons in the redox process. Therefore, I get 0.123 volts divided by 0.0257 volts over 2 is equal to the ln of K. I get that the ln of K is equal to 9.57 because voltages cancel. And then I get that K is equal to e to the power of 9.57, and I get that my K is equal to 1.4 times 10 to the power of 4, which should be D.